enolates are important reactive intermediates which can be made from carbonyl compounds with a hydrogen on the alpha position. We have seen before that carbonyl compounds with an alpha hydrogen are actually acidic because the corresponding conjugate base, which is the alpha carbonyl, is stabilized by resonance to give the corresponding enolate. Let's draw the structure, the general structure of an enolate of a ketone, something like this. This is the general structure of an enolate. Now, if you look at the structure of enolate, in the way it's drawn now, there is a negative charge on oxygen. So therefore, enolates are actually nucleophilic on oxygen, which means they can attack electrophiles on that position, if you like, on oxygen. And if that's the case, then this is one possible path for the reactions of enolates. That's when enolates attack electrophiles on oxygen. Now, this is called O-alkylation. O-alkylation, when the electrophile gets bonded to oxygen or when the nucleophilic oxygen attacks an electrophile. So this is called O-alkylation. And of course, alkylation, of course, is if the electrophile is typically an organic electrophile such as an alkyl halide. Now, that's one possible path, if you like, for the reactions of enolates. But enolates, not only they are nucleophilic on oxygen, obviously they are also nucleophilic on carbon, because you can do this by resonance, as we have seen before. To make enolates, of course, we begin with alpha carbanions. We can make the alpha carbanion back. So if we do resonance, then we can get something like this, where there is a carbanion on the alpha position. So clearly, enolates, not only they are nucleophilic on oxygen, they are also nucleophilic on the alpha carbon. So that's where actually their importance stems from. So this position is also nucleophilic, which means enolates can also attack electrophiles at the alpha position. So if that's the case, then this is another path for the reactions of enolates when enolates react with the electrophiles at the alpha position. So there is therefore C-alkylation. Okay, this is called C-alkylation as another possibility or another possible route for the chemistry of enolates. Now, this suggests that enolates are nucleophilic on oxygen and on the alpha carbon. Enolates can attack electrophiles at oxygen, and if they do, the reaction is called or described as O-alkylation. Enolates can also attack electrophiles on the alpha carbon, if they do, the reaction is described in general as C-alkylation. Now, C-alkylation is more common, so this route, if you like, or this path is more common than O-alkylation. This does not mean that O-alkylation is not possible. It is actually possible under certain conditions, and of course, C-alkylation is also possible under certain conditions. We will talk about conditions later on. For now, these are the two possibilities for enolates to undergo in terms of reactions, either O-alkylation in general or C-alkylation, but C-alkylation is more common. Now, it is more common because the product, which is that C-alkylation product, is thermodynamically more stable. This product is actually more stable thermodynamically than the O-alkylation product. So it's all about thermodynamics, if you like. So thermodynamics or nature favors formation or this route or this path, the C-alkylation path. This is of course due to the bond strength of the oxygen-carbon double bond versus oxygen single, and of course the CE, if you like, CC or CC here also versus the carbon-carbon double bond in the O-alkylation case. So it's all about bond strength actually, okay. The C-alkylation route or the C-alkylation product is thermodynamically more stable than the O alkylation product, and that's why C alkylation is more common. To conclude here, enolates are not only nucleophilic on oxygen, but it is actually nucleophilic on carbon. Actually, the chemistry on carbon, or the alpha carbon, is by far the more common path in comparison with the chemistry on oxygen or O alkylation.